Okay, friends. So today, in day two, I guess, of correlation and data mining, we're going to focus a little bit more on the mining part than the correlation part, although they both really go hand in hand. As part of your homework from last time, if you did it, you Googled correlation. I'd like to take a few minutes right now and actually do that with you as well. All right, so correlation. All right. Now let's see what correlation comes out. Oh, look at this. This is a fun window. Correlation and dependence. Oh, there's some neat images here. I'm not going to get into that right now. In statistics, correlation or dependence is any statistical relationship, whether causal or not, oh, I like this, between two random variables or bivariate data. You know what? We're just going to focus on that sentence. In later stat classes, if you go past Math 105, you'll study this in a lot greater detail. But really, I like some of the phrases here. I like bivariate data. I like that a whole lot. That just means that you have each data point has two dimensions, as we talked about yesterday. You've got an X and a Y, or a run and a rise. Statistical association, which sounds scary, but all that means is there is a dependence, which means as one variable is changing, the other one is changing in somewhat of a predictable way. Now, let's actually just look at some examples of data points that are correlated. Okay, so one type of correlation you can have is called a positive correlation. In English, what that means is you've got two variables. You've got an X and a Y, or a run and a rise. Bivariate. Bivariate just meaning two variables. As one of those variables goes up, the other one also goes up. Or another way of looking at it is as one goes down, the other goes down. But I think we read left to right for the most part. Here's what one could look like. All right, so here, this is one of my favorite data sets of all time. I went to a stat conference about 10 years ago and saw this one. They've got an observatory at Mauna Loa in Hawaii, the top of Mauna Loa, and they keep track of atmospheric CO2. So you can see that as the year, which is one variable, is increasing, the atmospheric CO2 on average is also increasing. So you can see this black line right there is trending upward. Atmospheric CO2 is positively correlated with the year. As the year goes up, atmospheric CO2 goes up. What I like an awful lot about this particular graph are these little wiggles within each year. So you might notice that there's little red, it's kind of like cyclical. And what's actually cool about that is they're keeping track of it with the seasons, because even Hawaii, which has a notoriously stable climate, it does have seasons. And there's a dormant season and a growing season. And during the growing season, that's when you'd be down in the lower CO2 levels. And in the dormant season, you'd be in the upper CO2 levels. The overriding trend is positive. It's a positive correlation because as year is going up, so is atmospheric CO2. Kind of a cool little correlation. I like the graphic too. It's from NOAA and the Mauna Loa Observatory. All right, here's one that's a little bit messier. But I like messy just because messy is oftentimes more realistic. What this is, it's a little hard to see, and I apologize for the blurry text here. What we've done is we've taken men and women in this study right here. I've given you all the links to all these studies in the video. And we're looking at body mass index, BMI, and comparing that to percent body fat. Now, in case you're unfamiliar with these measures, I'll just give you a quick and easy introduction. Body mass index is a number that is gotten by taking your height and your weight and doing a mathematical thing to it. I forget exactly what it is because I always use the online calculators to calculate it for me. We're going to talk more about BMI later in the statistics section of our course. So BMI, body mass index, and percent body fat. Percent body fat is actually a more mathematical, I think a more healthful mathematical measure. All they do here is they take measurements, usually body fat caliper measurements, or sometimes you can do hydrostatic testing. And they figure out of the 100% of your body, which is made up of bones and muscles and organs and fat, what percent of your body is actually fat. based on these measurements. And so don't worry too much about how either of these things is calculated. We'll talk more about it later. What I'm interested in most is as body mass index goes up, you're seeing that this cloud of blue is trending upward as well. So as BMI goes up, so does percent body fat. There's definitely a diagonal kind of tilt. Some people will argue that it's not so much a line as it is kind of a curve. But whether it's a line or a curve, it's going upward, left to right. It's heading upward. Women are higher than men for very simple reasons. Women have more fatty tissue on average than men, and they should have more fatty tissue on average than men. So that's why the women's group is above here. But both groups are trending upward. That's a positive correlation, a very good example of one. It's messy. It's messier than the Mauna Loa data because it's more scattered. We'll talk about that in a later video. Okay, how about a negative correlation? Negative can be thought of just like slope. This source, sorry about this little source is over here sideways. I'll just give you the graph right here. This means as the independent variable goes up, the dependent variable goes down. So as one variable goes up, the other one goes down. So what you're seeing is males and females from 1975 to 2018, teenage motor vehicle crash, deaths by gender. So you can see that both females and males, on average, deaths are dropping from 1975 to 2018. Here's your source over here for the data if you want it. Now, please notice we are not answering or even asking the question why this is happening. There are many theories as to why this is happening. We're also not asking a question, why were there more males dying in 1975 and why are there still more males dying in 2018 than females? We're not asking those questions. Those are wonderfully rich questions for psychology classes, for public health classes. Great. All we're trying to focus on right now is looking at this data and realizing, there's a downward trend. There's a downward trend. So that is a very, very good example of negative correlation. As time has increased, teenage motor vehicle crash deaths have decreased. Okay. Here's a slightly messier example of one. Also dealing with cars. We're graphing the curb weight of a passenger vehicle. That's just how much it weighs. 1,500 pounds, 2,000 pounds, 2,500 pounds. And then we're putting on the vertical axis the highway miles per gallon of a passenger vehicle. And you notice it's dropping down. As the car gets heavier, its mileage gets worse. This should make sense. Part of a fuel economy is having to overcome inertia. And a heavier car is going to take more fuel to overcome from being stopped than a lighter car is. So it makes sense that lighter cars should get better mileage than heavier cars. Look at me. I'm trying to explain the negative correlation instead of just admitting that there is a negative correlation, and that's totally fine. Okay, so that's just a really quick, very beginning look at correlations. Positive or negative. Positive just means the data is trending upward, left to right. Negative means it's trending downward. We'll do some data mining next.